Welcome back to the deep dive. We spent a lot of time talking about health trends, new diets, biohacking, all that stuff on the surface. But today, I want to go deeper. I want to open up the hood of the human machine and actually look at the engine.
It's about time.
Mhm.
People tend to see biochemistry as this scary, abstract subject, just hexagons and arrows on a page. But really, it's the operating system of life. You can't understand why you get sick or how a drug works without looking at the code.
And that is exactly our mission today. We're diving into a stack of resources that are, well, they're basically the Bible for medical students. The Lippincott Illustrated Reviews flashcards for biochemistry.
Right.
But we aren't here to memorize structures for a test. We're here to take those hundreds of cards and weave them into a story about how the body actually works and the chaos that happens when the chemistry breaks.
That's the best way to learn it. I mean, biochemistry isn't static. It's a story of flow, of energy, and regulation. And usually, we only notice it when a pathway gets blocked or, an enzyme goes missing. That's when the patient shows up in the emergency room.
Okay, so let's start at the very, very beginning. Before we even get to organs, we have to deal with basic chemistry. I was looking at this first section, the chemical foundation, and there's this card on aspirin. It explains something I never really got. Why does aspirin actually work when you swallow it?
It's a great place to start, actually, because it relies on a fundamental principle called the Henderson-Hasselbalch equation.
Okay, that sounds intimidating already.
I know, but don't let the name scare you. It's really just about pH and how things move across barriers.
Right, because for a drug to work, it has to get from your stomach into your blood. And to do that, it has to cross a membrane.
Exactly. And biological membranes are made of lipids fat. So as a general rule, charged molecules, things with a plus or a minus on them, they just bounce right off of fat. They can't get through. Only uncharged, neutral molecules can slip past.
Okay, so the goal is to be neutral.
Correct. Now think about the environment. The stomach is an acid bath. It's got a pH of, maybe 1.5. Aspirin itself is a weak acid. When you put a weak acid into a strong acid environment, like the stomach, something interesting happens. The aspirin molecule, it picks up a proton, a hydrogen ion.
And see, this is the part that always confuses me. I always think adding a proton means adding a positive charge.
In many cases, yes, but think of an acid as a molecule that's sort of holding on to a proton. When it has that proton attached, it's neutral. When it gives the proton away, then it becomes negative. And because the stomach is already so full of protons, the aspirin just holds on to its own. It stays protonated.
Which means it stays neutral.
Exactly. And because it's neutral, it's like a ghost walking through a wall. It slips right through that lipid lining of the stomach and into the bloodstream. If the stomach were alkaline, the opposite would happen. The aspirin would lose its proton, become negatively charged, and it'd be stuck.
So the stomach's acidity is actually a crucial part of the delivery system. That's wild. But once that aspirin or oxygen or whatever gets into the blood, it needs a vehicle. And that brings us to hemoglobin.
The protein that makes blood red.
Yeah. And the sources highlight this really fascinating difference between adult hemoglobin and fetal hemoglobin. I always just assumed they were the same. But the flashcards call HbF, the fetal version, a high affinity variant. Why? Why the difference?
It all comes down to a molecular tug of war. Just think about the situation. The fetus is in the womb. It can't breathe. It relies entirely on the mother's blood to deliver oxygen. But oxygen doesn't just, hop over to the baby out of kindness. It has to be taken.
So the baby has to be stronger than the mom, chemically speaking.
Chemically, yes. Adult hemoglobin has this little safety feature. It binds to a regulator molecule called 2-country BPG. Think of 2-country 3-BPG as a pair of handcuffs that makes hemoglobin let go of oxygen a bit easier.
Okay, a regulator.
Exactly. Fetal hemoglobin, on the other hand, it completely ignores those handcuffs. It doesn't bind to 2-country 3-BPG at all. So because it ignores the regulator, it holds on to oxygen with this incredibly tight grip. When the mother's blood flows past the placenta, the baby's hemoglobin literally rips the oxygen off the mother's.
That's basically parasitic survival at a molecular level.
It is. If they had the same affinity, oxygen would just reach an equilibrium and the fetus might starve. The system is rigged for the baby to win.
Speaking of hemoglobin, we have to talk about how we monitor it in disease. Anyone who knows a diabetic has heard the term HbA1c. I used to think it was just a random marker, but the chemistry is actually pretty intuitive.
It is. It's basically the sugar coating of your cells. The technical term is non-enzymatic glycosylation.
That's a mouthful.
It just means that if you have a lot of sugar floating around in your blood, some of it is going to stick to proteins, naturally. It's like spilling syrup on a counter. Things just get sticky. The hemoglobin inside your red blood cells gets, well, frosted with sugar.
And since we know how long a red blood cell lives,
Right, about 120 days, 3 months. So when we measure HbA1c, we're measuring how much sugar has stuck to that hemoglobin over its entire lifespan. It's not a snapshot of your blood sugar today. It's like a security camera recording of the last 3 months.
which is why you can't cheat on an HbA1c test by eating a salad the day before.
Exactly. The evidence is baked right in.
Now, sometimes the problem isn't sugar sticking to hemoglobin, but the hemoglobin itself being built wrong. This brings us to sickle cell disease. The cards compare it to another condition, HBC disease. They both happen at the exact same spot on the DNA, right?
They do. It's a specific position on the beta chain. Normally, there's an amino acid there called glutamate. Glutamate is polar, it loves water, and blood is mostly water, so that works great.
But in sickle cell,
In sickle cell, a mutation swaps that glutamate for a different one, valine. And valine is hydrophobic. It hates water. It's like oil. So when that hemoglobin is floating around, that oily valine spot is panicking. It wants to hide from the water.
so what does it do?
It finds another hemoglobin molecule and sticks to it, trying to bury that oily valine on the inside. This causes all the hemoglobin molecules to stack up into these long, rigid rods. And those rods stretch the red blood cell out of shape, turning it into that classic sickle,
And those stiff cells get stuck in tiny capillaries.
causing incredible pain, tissue damage. Now, contrast that with HBC disease. In that case, the glutamate is swapped for lysine. But lysine is polar, just like glutamate. It doesn't hate water, so it doesn't cause that clumping. It can cause a mild anemia, but you don't get the horrible crisis you see in sickle cell.
Wow. It's amazing that changing one single letter in the genetic code 1 amino acid is the difference between a mild condition and a life-threatening disease.
That's the fragility of the code.
I want to touch on one more hemoglobin story from the case studies because it's terrifying. Carbon monoxide poisoning. The case mentioned a woman with a kerosene heater who had a headache, but her skin was described as cherry red.
That's the classic deceptive sign. We usually think of suffocation making you look blue, cyanotic. But carbon monoxide is a master of disguise. It binds to hemoglobin 200 times more tightly than oxygen does.
200 times.
It bullies oxygen right out of its seat. But here's the trick. When carbon monoxide binds to hemoglobin, the complex looks bright red, brighter even than oxygenated blood. So the patient is suffocating at a cellular level, their tissues are starving, but to the naked eye, they look flushed and healthy.
That is a chilling visual. So we've talked about blood delivering oxygen, but what about the pump? Let's follow that blood to the heart. When a patient comes in with chest pain, how do we use biochemistry to know if they're actually having a heart attack?
We look for debris. You have to remember, inside a heart muscle cell, there are specific proteins doing the heavy lifting, and those proteins are supposed to stay inside the cell.
So if we see them in the blood,
It means the cell has burst. It's undergone necrosis, cell death. The membrane ruptured, and it spilled its contents into the bloodstream. The two markers we watch are CKMB and troponin.
but they don't show up at the same time, do they?
No, and that difference is clinically vital. Troponin is the gold standard. It's incredibly sensitive. It rises within a few hours, and it stays elevated for a long time, up to 10 days.
So it's the detective that hangs around the crime scene for a while.
Right. But imagine this. A patient has a heart attack on the 1st of the month. Their troponin spikes. On the 5th of the month, they feel chest pain again. If you check their troponin, it's still going to be high from that first attack. It tells you nothing new.
So you're flying blind.
Unless you check CKMB. CKMB is an enzyme that rises fast, but also clears out fast, usually within about 3 days. So if you check that CKMB on day 5 and it's high, that's new. That tells you it's a reinfarction.
That's a really practical application of enzyme kinetics. Now, taking a step back, why do those heart cells die in the first place? Usually they ran out of oxygen, which means that they ran out of energy. This brings us to the engine room, metabolism.
Powerhouse.
The sources spend a lot of time on glycolysis breaking down sugar, and they mention a condition called pyruvate kinase deficiency. Apparently, this is a huge problem specifically for red blood cells. Why them?
Because red blood cells are minimalists. To make room for all that hemoglobin, they threw out almost everything else, including their mitochondria.
Wait, they don't have mitochondria?
None. And since mitochondria are where we use oxygen to make massive amounts of energy, red blood cells just can't do that. They rely 100% on glycolysis, that simple, primitive way of making ATP from sugar.
So they are living paycheck to paycheck on energy.
Exactly. And pyruvate kinase is a key enzyme in that payout phase. If that enzyme is defective, the red blood cell makes zero energy. The pumps fail, the membrane collapses, and the cell bursts. We call that hemolytic anemia.
Wow. Other cells have backup generators, but the RBC just dies. Now, for the cells that do have mitochondria, they feed that sugar into the TCA cycle, the Krebs cycle. And there's a strong nutritional link here with alcohol, isn't there?
There is. The bridge between glycolysis and the TCA cycle is an enzyme called PDH. But PDH is needy. It requires a cofactor. It needs thiamine, vitamin B1.
And alcoholics tend to be deficient in B1.
Frequently. Alcohol inhibits thiamine absorption, and the diet is often poor. Without thiamine, you can't run the TCA cycle. Your brain, which uses a ton of energy, starts to fail. And this leads to Wernicke-Korsakoff syndrome.
That's the condition with the confusion and memory loss, right?
Yes, psychosis, ataxia, that wobbly walk, and encephalopathy. It's essentially a metabolic energy crisis in the brain because the spark plug, the thiamine, is missing.
Now, sometimes we aren't burning sugar. We need to make it. Gluconeogenesis, the body making fuel from scratch during a fast. But the flashcards have this big warning label on one molecule, acetyl-CoA.
This is a fundamental rule of human biochemistry. You can turn sugar into fat. We all know that. That happens via acetyl-CoA. But you cannot turn fat back into sugar.
Why is it a one-way street?
Because the reaction that turns pyruvate, the end of sugar breakdown, into acetyl-CoA is irreversible.
Yeah.
Once you're acetyl-CoA, you have two choices. Burn for energy in the TCA cycle or turn into fat. You cannot climb back up the ladder to become glucose.
So when you're fasting, your body has to scavenge other things.
Right. It uses amino acids from muscle, lactate, glycerol. But it can't just melt down your fat stores and turn them directly into blood sugar.
Speaking of sugar storage, we have glycogen stored in the liver and muscles. But the cards describe the muscle as being surprisingly selfish.
It is. The liver is the altruist. When blood sugar drops, the liver breaks down its glycogen and releases glucose into the blood for the brain, for everyone.
And the muscle.
The muscle lacks the specific enzyme, glucose 6-phosphatase, that's needed to release that sugar. So once glucose goes into a muscle cell, it is trapped. It stays there to power that specific muscle.
It's like a roach motel for sugar. It checks in, but it doesn't check out.
Perfectly put. And that's why in McArdle disease, where patients can't break down muscle glycogen, they get severe cramps and exercise intolerance. They're sitting on a gold mine of fuel they can't access.
Let's shift gears from sugar to the other fuel, lipids, fats. There's a specific application here involving premature babies and their lungs. What does fat have to do with breathing?
It's all about surface tension. Imagine a wet plastic bag. If you press the sides together, they stick, right? It's hard to pull them apart.
Right.
Your lungs are millions of tiny wet bags called alveoli. Naturally, they want to collapse and stick shut. To prevent this, the body produces a grease called surfactant. It's a phospholipid mix that coats the inside of the lungs and prevents that sticking.
Now, premature babies don't have this yet.
They might not. We can gauge lung maturity by looking at the amniotic fluid. We measure the ratio of two lipids, lecithin and sphingomyelin. As the fetus grows, lecithin production skyrockets. If that ratio is high, specifically over 2.0, the lungs are ready.
And if it's low,
then the baby is at high risk for respiratory distress syndrome. Every single breath is a struggle against that surface tension.
moving from good fats to the ones we worry about. Cholesterol, we have the bad LDL and the good HDL. I want to focus on the drugs we use for it, though. Statins. They're some of the most prescribed drugs in the world. What's the mechanism?
Statins are a master class in supply chain management. Your liver makes cholesterol. The assembly line has a boss, a rate-limiting enzyme called HMG-CoA reductase. It determines how fast the factory runs.
And statins take up the boss?
They inhibit that enzyme specifically. If you block the rate-limiting step, the whole production line just shuts down. The liver then realizes it's low on cholesterol, so it starts pulling LDL, the bad cholesterol, out of your blood to restock.
So it lowers blood cholesterol by tricking the liver into cleaning it up.
Precisely.
Okay, let's talk waste management. We eat protein, break it down, and we end up with nitrogen waste. This leads to some really distinct diseases. One caught my eye because of a very specific smell.
Maple syrup urine disease.
It sounds like a joke, but it's serious.
Oh, very serious. It's a genetic defect where the body can't break down what are called branched-chain amino acids, leucine, isoleucine, and valine. These build up in the blood and spill into the urine. And one of the metabolites smells exactly like burnt sugar or maple syrup.
So the diagnosis is literally in the diaper.
Often, yes. Yeah. And if it's untreated, it causes severe neurological damage.
Then there's the pain connection. Gout. The classic image is the older man with a swollen, agonizingly painful big toe What is actually happening in that joint?
It's a precipitation event. Gout is caused by uric acid, which is a waste product from breaking down purines. If uric acid levels get too high in the blood, it stops dissolving. It forms crystals.
And these aren't soft, fluffy crystals.
No, they're described as needle-shaped. So just imagine microscopic needles forming inside your joint space. The immune system attacks them, causing massive inflammation. That's the pain.
And the drug allopurinol helps because
It inhibits the enzyme xanthine oxidase, which is the machine that makes the uric acid. You turn off the faucet, the levels drop, and the crystals dissolve.
I want to make sure we give enough time to the blueprint itself, DNA, the central dogma. The cards discuss how fragile our DNA actually is, especially with sunlight.
We deal with this every time we step outside. UV radiation is like a little hammer hitting your DNA. It causes two adjacent bases, usually thymines, to fuse together. We call them pyrimidine dimers. It creates a kink in the DNA ladder.
But usually we fix it.
Constantly. We have a system called nucleotide excision repair that literally cuts out the damaged section and patches it. But in a disease called xeroderma pigmentosum, that repair crew is missing.
So the damage just accumulates.
Rapidly. These patients are incredibly sensitive to sunlight. They can get multiple skin cancers by the time they're children because every minute of sun exposure creates permanent mutations.
On the flip side, we can use DNA for diagnosis. We hear about PCR all the time, but how does it actually find a disease like cystic fibrosis?
Think of PCR as a molecular photocopier. Suppose you're looking for one specific typo in a massive encyclopedia like the delta F508 mutation in cystic fibrosis.
Yeah.
You can't see with the naked eye.
So you copy the page.
You copy that specific page 1 billion times. You heat the DNA to split it, cool it so markers can attach, and heat it again to build a copy. You cycle this over and over. Suddenly you have a bucket full of that one gene segment, and you can easily test if the mutation is there.
It's finding a needle in a haystack by turning the needle into a haystack.
That's a great way to put it.
Finally, let's close the loop with vitamins and clotting. We touched on B1, but the B12 versus folate story is a classic medical trap.
It is. Both vitamin B12 and folate deficiencies cause the exact same looking anemia, megaloblastic anemia. The red blood cells get huge.
So if a patient has big RBCs, you might just give them folate and call it a day.
And that is incredibly dangerous. Because while folate will fix the anemia, it will do nothing for the other thing B12 does. B12 is required to maintain the myelin sheath on your nerves.
So if you miss the B12 deficiency,
The patient's anemia gets better, but their nerves continue to rot. They can develop permanent dementia and spinal degeneration. You've essentially masked the warning sign while the fire burns down the house.
that is a critical distinction. And lastly, stopping the flow. Blood clotting. We have vitamin K and the drug warfarin.
Vitamin K is the activator. It adds a chemical group to certain clotting factors that allows them to stick to calcium and form a clot. Warfarin works by sabotage. It inhibits the enzyme that recycles vitamin K.
So the liver runs out of ammo.
Exactly. It produces clotting factors that are just duds. They can't stick together.
But if a clot is already there, like in a stroke, warfarin won't help, will it? You need something stronger.
You need a clot buster. That's TPA. It activates a molecule called plasmin, which is like a molecular pair of scissors. It goes in and actually cuts the mesh, holding the clot together, dissolving it.
It's amazing. We've gone from the pH of the stomach to molecular scissors dissolving clots. It really shows that the body isn't just a collection of organs. It's a chemistry set in constant motion.
It is. And understanding that chemistry is the only way to really fix it when it breaks.
Before we wrap up, let's try to bring this into the real world. I want to pose a scenario to you and to everyone listening. Let's see if we can apply what we learned.
Let's hear it.
You're in the ER. A patient comes in clutching their chest. You run labs, and both CKMB and troponin are sky high. It's a heart attack. You treat them, they stabilize.
Okay.
3 weeks later, the same guy is back. He's complaining of chest pain again. You're worried he's having a second heart attack. You order the labs. The troponin is still somewhat elevated, but the CKMB is normal. Is he having another heart attack?
This is the timeline question. Remember, troponin is the ghost. It lingers for 10 days, sometimes more, but at 3 weeks, it should be on its way down. The key is the CKMB.
Because CKMB clears out in 3 days.
Right. If you were having a new heart attack right now, that CKMB would be spiking again. Since it's normal, The pain is likely not a new necrosis event. You've successfully ruled out a reinfarction using enzyme kinetics.
And that is the power of knowing the mechanism.
Yeah,
Thank you so much for walking us through the blueprint today. It definitely makes the invisible world of biochemistry feel a lot more tangible.
my pleasure. Just remember,
I-
every symptom has a molecule behind it.
Thanks for listening to the deep dive. We'll catch you on the next one.